Okay, now you can start. Thank you.
Okay, thank you, Ines. Hello, everyone. My name is Vincent Westrofer, and I'm part of the PeneloPe project, which is a European project. And I will present you a training session on motion capture hardware and software and ergonomics evaluation. Some words about myself. So I'm a French engineer. I got a PhD from MINParisTech almost 10 years ago. And since then, I've been a research engineer at CEA List next to Paris. And the lab in which I'm working is mainly focused on digital twins, interactive digital twins, and it gathers plenty of topics such as real-time physics simulation, human-robot interaction, industrial robotic applications, motion capture, VR training. And I'm involved in plenty of industrial projects, European projects, national projects, and I'm also mentoring some PhD and interns in the lab. And today we will really focus on motion capture and ergonomics evaluation. Some details about the training. So it will last about 2 hours and a half. It will also include some questions if needed. The main profile of the people attending this training session is mostly dedicated to beginners. So engineers, ergonomists, operators, but it will mainly be an introduction to motion capture and ergonomics evaluation. So we will not go into really fine details, but we will actually have a broad view of these topics. At the end of the session, you will be able to watch again the video. The presentation is recorded, and we will also provide the PowerPoint materials so that you can see it afterwards also. About the agenda, so here you have a schema about the topics we will focus. So motion capture data, digital human control, ergonomics assessment, and it will be divided in 6 main sections. So first we'll focus on motion capture hardware, then on motion capture software. Then we will have some sections dedicated to digital human models and digital human control. And at the end, we will really focus on ergonomics assessment. And we will also have a short section dedicated to exoskeleton evaluation, as it is also a research topic inside the PeneloPe project. So we will give you some insights and details about what has been done for this project. So let's begin. If you have some questions, please feel free to ask them during the training session. It's better if we can see it as an interactive discussion rather than only myself talking. So please feel free to ask questions either in the chat or orally. So first, some section about motion capture data and motion capture hardware. So basically, motion capture is used to capture the motions of a user, of a person, and we can actually divide it into 2 main families of hardware. On the one hand, you can have sensor-based hardware, and on the other hand, you can have markerless hardware. So sensor-based hardware, well, the idea is that you put sensors on the human body in order to capture the body movements in space. And the markerless hardware is mostly using cameras. So it can be depth cameras or iPhones or monocular cameras, so that you don't put sensors on the body, but you use only the video to track the human body. And in the presentation, I will give you some videos and details about what each hardware can do and what are the advantages and the drawbacks of each hardware. So let's begin with first family of sensors. So it's actually focused on optical tracking with infrared cameras and sensors. So these sensors are mostly used sometimes in the cinema industry or in the video games industry in order to give and provide really precise animations and in order to track the body with high precision. So the idea is that you have in space some small spheres that can reflect the infrared light, and this infrared light will be provided by infrared cameras. At the end, you can get the 3D position of each sphere, and you can also gather these spheres into markers, and these markers will provide you a 3D position or 6D position, so a position and a rotation. You have plenty of examples of these technologies, ART tracking, OptiTrack, Vicon, Qualisys. These are quite expensive hardware. I would say for one camera, it can be 10,000 euros, for example. The main advantage is that you get really high precision with this hardware. The drawbacks is that it is really sensible to occlusions. If the spheres are occluded, then you cannot track them. The other drawback is also that it is a complex setup. As you can see on the image on the right, you have to put plenty of markers on the body. It's quite long to set up, and it's also not really user-friendly for the user wearing the sensors. And the other drawback is it's quite expensive. Here I can show you a video. So it's quite an old video. It was maybe in 2016. So it shows you an example with the ART tracking technology. Here we have, I guess, 4 infrared cameras, and they can track a set of 20 markers that you can see here on the video. So it's plenty of small spheres, and you track them in space, and in the end you can animate an avatar like the one we see in the video. So in my lab, we used to use this technology some years ago. Nowadays, we don't use it really so often. We prefer to use some new technologies now. An idea of new technologies we use is based on infrared leaders and sensors. The main example is the HTC Vive trackers, V2, V3, that you can see here. Actually, the principle is quite the same than the previous technology, but it's really
Okay, there must be an error. Vincent will come just in a moment. Yes, Vincent.
Yeah, sorry, I got disconnected, but I don't know why.
I don't know.
Sorry for that. Should be okay right now. So you should see my screen again. You can hear me.
Yes, we do.
Yeah. So sorry for that. So the idea about this tracking technology is the same than the one before. But it doesn't use really infrared cameras. It's only leaders. So it's infrared rays that project in space. And the sensors here, they are active sensors, and they track the LiDAR in space, so they can give a 3D and 6D position in space. You can also have customized trackers, like the Tundra trackers, the Manus trackers, so that you can have your own tracker configuration, like this one. The advantages of these trackers is that they are really low cost. It's mostly, I would say, 200 euros for one sensors. It's also VR ready. You can use it directly with VR headsets without any calibration. It's also really user-friendly. The main drawbacks is that it is also sensible to occlusions. The precision is not really high, so you got a 1 centimeter precision. And you also have to set up all the leaders in space. One example I can give to you is with this video. So it was done in our lab some years ago. So you can actually see. Okay, I will launch the video. Get some time. Okay, so here you have the tracking of the avatar. The blue cubes represent the trackers in space. So you have the complete 6D position of each tracker, so a position and a rotation. And thanks to this data, you can track an avatar in space. We will actually see how we can animate this avatar in the next sections. And based on these sensors, you can have also an ergonomics evaluation, as you can see in the video. And also, we will mainly focus on this ergonomics evaluation in the next sections also at the end of this morning. So as you can see, the quality is quite good. It's a really nice set of sensors for people wanting to have basic avatar animation. Recently, there has been some new kind of sensors that we can call inside-out sensors. Inside-out means that it's the tracker which tracks itself without any cameras in space. Actually, the cameras are embedded inside the sensor, as you can see on the image here on the HTC Vive Ultimate trackers. So there are two cameras at each side of the sensor. And so with SLAM technology, the tracker can track itself in space. So it's a really intelligent way of having tracking sensors. It's quite new. For now, HTC is the only one providing this kind of sensor, but it's the same technology that you can have on VR headsets. Any VR headsets is now localizing with the SLAM technology and embedded cameras. So the technology is not new. The main advantages of these sensors is that it is also low cost. I would say one sensor can be between 100 and 200 euros. It's also VR ready. You can use it with your VR headsets really easily. And it doesn't require any camera setup in space. So it's really convenient to use. The main drawbacks are it's also sensible to occlusions. If the cameras are occluded, then the sensor cannot give a correct position. And also the precision is quite average. So I would say 1 centimeter, which is quite enough for plenty of applications. One example is shown here in our lab. This is quite recent. It was done 1 month ago. So the idea is the same. The blue cubes represent the 6D position of the trackers in space. Here we use 5 trackers. we have a short calibration process in order to know the referential of the sensors. So here we calibrate the origin of the sensors. Then we put back the belt. And at the end, we also have a short calibration procedure for calibrating the rotation of the sensors. And at the end, in just one click, we can have an animation of an avatar like this one. So it's a Ready Player Me avatar. But as you can see, the animation is quite good for having a basic animation. This kind of sensors is really good. You can also track in large areas, like the one you see in the video. It's our VR room in our lab. You can track all the legs, you can track the arms. So it's a good technology. So for now, I presented you basically sensors with the optical tracking, so based on cameras. The other family, based also on sensors, is the inertial measurement units, so IMUs. It's and inertial suits. So these sensors, they contain an accelerometer, a gyroscope, and also a magnetometer. And at the end, they can provide you information about 3D rotation. So these sensors only give you rotations. The idea is that you put plenty of these sensors on the human body so that you can get the angulation of each bones of the human body. So that's why we speak about inertial suits. Inertial suits, they are actually a collection of 17 to 20 sensors. You put them on the body, and at the end, you have the complete human motion. This is really also, it's really used in also the cinema or animation of video games. It's a really good hardware. Some examples are the Xsense sensors. So the orange one you can see at the top of the slide. Another good suit is also the perception neuron one that you can see at the bottom of the slide. The main advantages of this technology is that it is not sensible to occlusion, contrary to camera and camera-based sensors. So even if the human body is not seen, you can continue to track the human body. The other advantage of this technology is that you can get really high precision on the movements of the human body. The main drawbacks of this technology is it's sensible to drift, so it cannot really give you precise absolute position in space. It only provides you rotation, and these rotations can also drift in time. The other drawback is that it is also sensible to electromagnetic disturbance. So if your environment is made of metal, then you can have issues when using these sensors because the rotation they provide will be disturbed. The other drawback is also it's quite a complex setup. You have to put mostly 20 sensors on the human body. So sometimes it's not really possible to put them on operators in the industry. It's time consuming, and sometimes it's not allowed also on the workstation. One example I can give you, so it's also done in our lab. It's quite a recent video. So here I'm using an Xsense suit with, I would say, maybe 17 sensors on the human body. And I'm also using it with a VR headset. So here it's HTC Focus 3. So we can combine the two. And as you can see, the global posture of the avatar is really well represented. You can crouch on the floor. The sensors will still track. You can move in space, so that there is no occlusion issues. You can also track in a large space. And what I'm showing next at the video is that we can also use the VR controllers to give additional data for the hands, for example. And we can finally track physics human body, as you can see now, in order to superpose to the XSense avatar. We can actually control physics human body on it. This is something we will see later on in the presentation, but you can see what we can do now. Another kind of sensor is electromagnetic sensors. So the main idea is that you have an electromagnetic field that is generated by a certain part, and then you can track electromagnetic sensors relative to this basis. This is quite an old technology. Maybe some of you know the Polemus sensors. It was used maybe 15 years ago or 20 years ago. This technology was also used in more recent hardware, like the Razer Hydra controllers that you can see on this picture here. There was also a tentative of having more industrial sensors like the 6N stem. I think it didn't work, so they didn't industrialize these sensors. But a really recent example of electromagnetic sensors is actually used in the Manus quantum gloves. So that actually the idea is that you have an electromagnetic field generated at the origin of this magnetic field is somewhere on the wrist. And then each fingertip is an electromagnetic sensor that is tracked relative to this basis. The main advantage of these sensors is that it's not sensible to occlusion.
Yeah, we can see you now again. But you're muted.
Yeah, it's better like that. Sorry
Thank
about
you.
that again. I hope it will not be like that during the whole presentation, but hopefully I can connect again really easily. So sorry if it happens again. So the Manus quantum gloves, they give really high precision about the fingertip position relative to the wrist. The main drawback of this technology is electromagnetic disturbances, since it's based on generating an electromagnetic field. If you also have another electromagnetic field in your environment, then you will have disturbances, and the sensors will give you some incorrect position in space. The other drawback is also that it's you can only track in reduced areas because you have to keep yourself inside the electromagnetic field generated by your basis. At the end, you get some 6D position of the markers, so position and rotation. Okay, so for now we have seen really one big family of sensors, so of family of hardware based on sensors and cameras. And now we will switch to the second family of hardware, which is focused on cameras and markerless technology. So the first cameras that I will present to you is depth cameras and also stereo cameras. Some example that you know is the Kinect V2, the Kinect Azure. You also have the Stereolabs Z2i. These cameras, they provide you with a depth map of the environment, and based on this depth map, they're able to segment the human bodies seen by the camera, and inside this segmentation, they are able to extract 3D skeleton. As you can see on the pictures here, the bottom picture is a short video of the Stereolabs Z2i camera that showing to you that you can track multiple avatars, multiple people, and for each of these people, you can get a skeleton. The advantage of this hardware is that it requires no sensors, and it's also low cost. One camera is something between 300 and 400 euros. Okay. The main drawbacks, it's of course it's sensible to occlusions. If the camera only see a part of the human body, then it cannot track correctly, and also the precision is not always good. I would say that you get a 1 centimeter precision, um, depending on the situations, and it also depends on how far the human body is from the camera. I can show you a video here about the Z2i tracking made in our lab also. So here the camera is at the viewpoint you see here. We can scan the morphology of the user so that it corresponds to the exact morphology of the people the camera is seeing. And then in real time, you have the 3D skeleton, and you can have an avatar following the movements, like here. And then the principle is the same. You can also extract an ergonomics evaluation based on the movements. I guess that's what we can see in the second part of the video right now. So based on the colors here, they show different ergonomics levels based on the current posture of the user. Another application and a video I can show you is that in order to solve the occlusion problem, if you use only one camera, then it's sensible to occlusions. Well, the solution is to use multiple cameras in space, and this video is showing you that the use case with 3 Kinect Azure. So depending on where the user is located, we can use the information of different cameras. So here the user is occluded by a wall, but at least one camera can see the user. So in the end, we can fuse the data of these different viewpoints and get a correct tracking of the human body. The different colors you see at the beginning of the video, they are the tracking points of each viewpoint of each camera. So the right dots are the fused skeleton, while the color, green, red, blue, they are the tracking skeleton of each camera. So here you can see that the green is from one viewpoint, the blue is from the other viewpoint, etc. So it's an interesting use case here. to go on with the cameras, now there is a really interesting trend and interesting technologies which is becoming more and more developed, which is based on monocular cameras such as phones. And by adding AI technology and deep learning, you can actually extract the human body movements based only on one viewpoint and one monocular viewpoint, such as a phone. So it's the advantage of this technique is that it's really easy to set up. It also requires no sensors. It's also low cost. It's only one camera. Um, well, and the drawbacks are the same than the previous section, is that it's sensible to occlusions and it gives you a low precision. Some examples are the Move.ai platform, the Radical Motion platform, also movers. And for 2D skeleton, you probably know the Open Pose library that provides you a 2D skeleton based on a single camera viewpoint. So these are emerging technologies that we are also currently studying in our lab. For motion capture hardware, I wanted to focus also on hand tracking. Just one slide. For hand tracking, you have basically the same technology, either markerless cameras or sensor-based gloves in order to track the human fingers, the human hands. Example of markerless technologies, the Lip Motion 2, the Ultra Lip, and also now you have all these tracking technology integrated directly inside VR headsets, such as the Quest 3 from Meta or the Focus 3 from HTC. It's really common technology right now. For the gloves technology, the main provider for now is the Manus gloves. You can know probably about the Manus Prime. Manus Prime is mostly based on inertial measurement units and also flex sensors. The flex sensors, they can measure the finger bending. You also have the Manus Quantum technology, so based on electromagnetic sensors. They provide you with really precise fingertip movements. You can also get the Sense Glove, which is mostly based on cables, and it also provide you with a haptic feedback and force feedback. Some example of markerless cameras. Here it's the lip motion tracking used on a headset, on a VR headset. So it gives you really precise finger movements. You can use them afterwards inside the VR simulation. And at the bottom, I give you an example of the Manus Quantum motion capture with only one glove here. So the absolute position is provided by a HTC Vive tracker. And then relative to this global position, you can get the fingers movement. And as you can see, it's quite a precise technology. So if you require really precise movements, this kind of glove is the one you should actually use. Okay. As a conclusion on motion capture hardware, well, the important thing to understand is that adequate motion capture should be chosen depending on different factors. First, it should depend on the environment context. Are you in a VR room, which is free of every occlusion? Or are you do you want to track a human body in an industrial space in which you will have plenty of occlusions, plenty of electromagnetic disturbances? This environment can also be sensible to brightness. So first, you should focus on the environment you want to track. Then the other question you should ask yourself is about the intrusiveness of the hardware you want to use. Should it use sensors? Should it be markerless? Depending on the situation, you don't have the choice. For example, in the industry, the idea is not to disturb the operators. So you don't want to put sensors on the operators. So you will choose camera-based tracking. And the other question also you should consider is the price and also the precision. Do you want precise tracking or not? Okay, that was the first section of the training session about motion capture hardware. Now we will switch to motion capture software. Motion capture software is actually needed for several reasons. First, you need to connect to the hardware. You also need to calibrate the sensors and the cameras that you want to use. You also want to visualize the data, and at the end, you want to export or stream the data of the sensors to other software or to specific files. The idea is that actually, or unfortunately, each hardware comes with its own software integration. For example, Xsense has its own software. It's called Xsense Move and Animate or Xsense Move and Analyze. The perception neuron suite uses Axis Studio, to which you connect the suite and in which you calibrate the sensors and then you analyze the session. The ART cameras, you connect them through a software called D-Track, and then you can use the ART human software in order to calibrate the sensors on the human body. Another example is the OptiTrack. So the software is called Motive. That's what you see on the picture here. So this software will be able to track the small dots, infrared dots in space, and based on these dots, it will give you human reconstruction of the body that you can use afterwards. Another example is the Manus Core and Polygon software. So this is the software used by Manus to track gloves and also trackers in space. You also probably all know about SteamVR. SteamVR is the main driver used to connect VR headsets, VR controllers, and it's also SteamVR which is used to connect HTC Vive trackers and HTC Vive Ultimate trackers also. And actually, the list could be really longer as we can use plenty of hardware, and each hardware comes with its own software. Each software, usually, they can export standard animation data as FBX files, BVH files. These files are standard animation files. Also, normally, each software can also propose a set of different functionalities. The first one would be a software development kit, either in C++, in C#. If you want to integrate the hardware in your own customized integration and your own customized software. This software can also propose a proper integration into third-party software such as Maya, Autodesk Motion Builder, and most of the time, this software, this motion capture software, they provide a live stream to other third-party software, such as Unity or Unreal Engine, for example. And this is really important because normally people are really used to using their own animation software, such as Maya or Motion Builder. They're also used to use commonly known game engines such as Unity and Unreal Engine. So it's really important that motion capture software can provide integration inside these third-party softwares. Here on the picture on the right, I give you an example of the Manus Polygon and Manus Core software. As input, you get the tracking data of the human body and the tracking data of the gloves. And as outputs, this Manus Core is able to give you a FBX recording. They can also provide a SDK so that you can get all this data inside your own customized integration. And it also provides streaming functionalities to Unity, Unreal Engine, Motion Builder. So that's an example, but you actually get the same for Xsense Move and Animate, for example. They can provide you plenty of streaming opportunities. In the end, what is the nature of the data you can get? So first, you get plenty of position data, and the position data you get depends on the hardware. So sometimes it's only 3D points. So 3D point would be just a position in space. So it's a X, Y, Z position. That's the case of HTC Vive trackers, for example, or optical trackers. Some other hardware will only give you some 3D rotations in space, like the Xsense sensor. So this 3D rotation will be coded commonly as a quaternion. A quaternion would be X, Y, Z, and W values. It can also be Euler angles, depending on the data you want to access. You can also get a 6D markers. So 6D would be a position and a quaternion in space. And also this software, they can also give you the skeleton data. So the skeleton data would be a set of different 3D and 6D points in space, each point corresponding to a different body bone. The other data you would get would be marker IDs, so the 0, 1, 2, 3, 4, 5, in order to distinguish each marker with an ID. And also, usually, this motion capture software, they provide you with a detection confidence between 0% and 100%. 0% meaning that the body is not tracked at all, and 100% meaning that the software is 100% sure that the tracker is at this position. And then the intermediate confidence, like 50%, would mean that the software is not really sure that the sensor is at this correct position. Some, for example, because it's occluded or because it was not seen for a long time. And so then it's at your convenience to use the confidence score to trust or not the data that is provided by the motion capture software. You can also have some standards about the data that is provided. So I already talked about FBX and BVH file, which are really standard animation files. And for streaming functionalities, well, there is not really a standard, but nowadays it's important to know about OpenXR. So it's mostly used for trackers and for finger tracking and hand tracking. The OpenXR provides some standards about how to describe the data you want to share, but it's not really used by all this motion capture software. No, actually, not right now.